Hi there. Welcome to Xamarin University. My name is Mark Smith, and I'm going to walk you through garbage collection fundamentals when using .NET or Mono to run your applications. There's several things that we're going to look at. We're going to look at why we use a garbage collector and what advantage it holds for us. And then we're going to dive into what actually causes a garbage collection to occur and how you can see them happening in your application so that you know how to respond appropriately, or perhaps even set up your application to avoid garbage collections in some cases when you hit critical operations. We're going to talk about some of the optimizations that the GC system uses in both .NET and in Mono, and some of the things that you can do in your code to help make your application more responsive in the presence of a garbage collector. To start with, let's set a baseline for everyone. I'm sure that all of you are aware that .NET and Mono both use a garbage collector to reclaim memory that's used by your application. This garbage collector, sometimes referred to as a GC, periodically will stop your application, scan it, find all the memory that you've allocated but are no longer using, and free it so that your application can then continue to work appropriately. The implementations that we use in both Mono and .NET are very similar, and a lot of the things that we talk about in the course of this particular class will apply to either environment. But in some cases, we're going to delve a little deeper into the Mono specific implementation called sgen than we will into the .NET implementation. So why do we use a GC? Well, there's a couple of reasons. Most modern languages today actually provide some kind of GC-based system. And some of the reasons why are because it's very easy to work with. The language provides a new operator, but you don't have to worry about actually deleting anything. So there's no free or delete or any sort of operator to actually get rid of the memory that you've allocated. This makes it very simple, and it also stops some of the more common memory leaks that you might have inside of your application. Now let me be clear here. You won't actually get rid of every single memory leak in your application. There are some things that GC systems can't detect, and there are some situations you can get yourself into which actually cause a memory leak. We talk about those in the XAM370 class. But by and large, GC-based systems will reduce the types of memory leaks that you will happen, and certainly will remove the more common cases that you see in legacy languages like C or C++. And then finally, another advantage that we get out of GC-based systems is because it's organizing the memory for us, you often will get a bit of a performance boost related to how the CPU is actually reading memory. So things that were allocated together often are together in memory, and therefore when you read one of those items into the CPU cache, you often get the other pieces as well, with the assumption, of course, that when you allocate things together, you often use them together inside your application. So let's look at an example of actually seeing GC at work. So I'm in Xamarin Studio on a Mac. You can run this exact same project on Windows, and you can run it in any of the platforms. I'm actually going to use a console app just because it's a little easier to retrieve the data, but keep in mind that the Mono garbage collector that we're using here on the Mac is exactly the same Mono source code that runs in iOS and Xamarin Android. And so the idea behind this application is very simple. We're going to open a file called gcalex.csv on the desktop, and I'm going to run in a loop for 3 seconds. So you can see my little loop here, and I'm going to allocate an object. Now notice I'm not holding a reference to this object. I'm just throwing it away immediately, so it's going to get collected as part of the first pass. And the idea is that I'm going to dump out the address of this object. And so I've just got a little bit of unsafe code here to actually take the pointer address of where this object physically got allocated in memory. And I'm just going to dump out all the addresses to see if we see a pattern. And so let's go ahead and run it. It's going to run for 3 seconds. And it's going to throw our output onto the desktop. And so if we look here on the desktop, I can see there's a gcalex.csv. And I'm going to go ahead and open this with Microsoft Excel. And so here's our data. I'm going to select this first column here. And I'm going to say Insert. And let's go over here to the line charts. And let's go ahead and put a line chart in here using this data as our lines. And what I want you to notice here is this is the address of the object itself. And so if we expand this chart out a little bit, notice that what we have is allocation address going up. So it's just being allocated. And then suddenly we have this steep fall off. And then again, address is going up, and then a steep fall off, and address is going up, and a steep fall off. Now, what you're seeing here is GC at work. This steep drop-off right here is actually a garbage collection. And then notice that we just started over at the same basic address. And so if you look here, these addresses are going to be very, very similar. And we're just reusing this same block of memory each time. And the reason for that is we didn't hold any of those references. We allocated them and then we released them. And then the garbage collector kicked in at some point and it released all of those objects. All of those objects got freed. And so that memory segment is now free. And we begin to reallocate those objects. Now that you've seen the GC system at work, it's helpful to dive a little bit under the covers to see a couple of characteristics of it so that you can write your applications more efficiently to work with the GC system rather than against it. And there's really two things that you're going to be interested in. The first thing is, what triggers a GC? When does a GC actually occur? And how can we predict that? The second thing is, we want to reduce the time it takes to actually perform a GC. And so understanding what causes a GC and then the steps that it does when a garbage collection occurs are critical in sort of managing our expectations of what happens in our application. So let's start with what triggers a GC. To start with, when your application starts, the runtime allocates memory for you to use to allocate objects. And it essentially maintains a pointer into that memory that decides exactly where the free space starts. And when you do an allocation, the system will look at the object itself, it will determine how much space is required to hold that object and all of its instance parameters. It will then move the free pointer by that amount of memory, zero the memory out, and then return the previous location back to your application. This is in effect how the memory allocation system actually works. And your application will sit there and continue running on until we attempt to allocate an object that's too large for the free space that we have available. So in this particular case, we're attempting to allocate an object H, but we don't have enough space in our free heap to be able to actually hold that object. This is the point at which a garbage collection will kick in. And it happens on the current thread. So whatever the thread is that's allocating the memory, that's the thread that's going to be used or hijacked by the GC system to actually do its work. Now, it's important to recognize that while this GC happens, the system has to stop all the other threads. We're going to be moving objects around and fixing up pointers, and it would be disastrous for us to continue doing other things with some of those objects on other threads while we're moving them around. And so we call this a stop the world collector. The world literally stops in our app while a GC occurs. And so what happens? Well, the first thing the system has to do is it has to identify all of the things that your application is actually using at this point in time. We call these the live objects, and it does it by traversing something it calls routes. Routes are things that our application is using that points to a variety of objects. And you can think of it as a tree of objects. And so you can see that one of the routes that we'll use is our thread. And so it walks our current thread and it identifies all the objects that the current thread has access to and could use at this point in time. Now, this traversal is fairly smart in the sense that you can see that the pointer going from F to C isn't actually evaluated because the system recognizes that it's already seen the object C, and therefore that entire subgraph, anything that C actually pointed to, doesn't need to be evaluated twice. But all the objects that are no longer reachable, things that we don't necessarily have references to anymore, those are now considered dead objects. And these are the objects that are going to be collected by the garbage collector, and it's going to throw them away and then use the space that these objects were holding on to prior to the collection to be able to allocate new objects. So what is a route? Well, a route is essentially a live reference to an object that potentially points to other objects. And we have three places that the system looks at for routes. The first is static properties and fields. So any place in your application where you use a static, that's immediately considered a route because anywhere in our app we can actually access that reference. We also look at all of the objects that are on your thread stack. And so every single thread that's running in your application presumably has local values that it can access. And it will walk the thread stack and it will identify each of these. And these are considered routes. And it starts at each one of these and then walks every object graph that it can find to find all the live objects. And then finally, any object that we've passed into native code also has to be tracked. So these are things that we aren't necessarily holding on to, but we've given them into the native operating system, and so therefore it has access to them, and we certainly can't get rid of them at this point. Sometimes we call this pinned objects as well, because these are objects that we don't want to move, because there's no way to know exactly what the native operating system is doing with these. So the system's going to identify these routes from each of these three locations. It's going to walk every single reference that it can find, starting at each of these routes, and then it's going to take all the other things that are no longer being used, and it's going to collect those. And so it's going to look like this. These set of objects here are now considered dead and can be removed from memory. And the system will essentially collapse all the objects down. It then has a larger block of free space where it can now allocate our object H. Our pointer moves to the end of H, and then we continue running until, again, we run out of space. This GC process happens constantly in our application, so every allocation it's possible that we could have a GC that occurs. Now, the reality is, a GC doesn't happen on every single allocation. It happens in very specific cases based upon when we actually run out of space and a memory allocation can't be satisfied. That's the point at which a GC occurs, and it occurs on the thread that failed the allocation. Now, you can also request a garbage collection. We do that through the GC class. It's a static class and it has a set of properties and methods on it. And the one that you'll probably be most familiar with is the collect method. The collect method is a hint to the garbage collector to ask it to actually perform a garbage collection right here and now. Now, in Mono today, it's a little less of a hint and more of a command. It actually does run a collect anytime you call the collect method. And you may have heard the advice in .NET desktop programming that you generally should not call GC collect. And that's generally good advice. We really want the system to do the collections when it needs to, and we don't necessarily want to impinge upon that knowledge because we don't know what other threads are doing in the system. But there are some times that you may actually want to call GC collect yourself. In particular, in Xamarin Android, where we have two garbage collectors that are competing with each other, it's actually useful to periodically call GC collect, particularly if you've released a large object. So in this particular case here, notice that we've got some image that we've loaded. That image has a whole bunch of native memory potentially associated with it. And so by us setting the reference to null and then doing a GC collect, we can let the garbage collector go ahead and free that native handle, which will then go ahead and free all the native memory that's associated with the image. This can reduce our working set, and in a low-end Android device can actually be the difference between an out-of-memory condition where your app crashes or your app continuing to run. And so it is useful sometimes in the mobile world where we are somewhat resource constrained to still use GC collect periodically in our apps at predefined times where we know that it would be useful to do a collection. Now, be aware, in Mono, the GC class isn't quite the same. And so if you've used the GC static class in the .NET world, you may be familiar with some of the other methods and properties that it has. Well, the GC implementation in Mono isn't as fully developed or implemented, and so you'll find things like add memory pressure and remove memory pressure don't do anything. They don't throw an exception, but nothing actually happens. It doesn't do any tracking of that memory. The collect method is only partially implemented. So collect has several overrides that allow you to pass in the generation to collect, and there are other things that you can do as well. None of those features are actually implemented today in the SGen collector. Instead, it's just collect and all the other options are ignored. And then some of the more advanced options like wait for full GC approach or register for full GC notification, these features aren't implemented at all. And in fact, if you attempt to call them, they will throw an exception. And so be aware that there are differences. And so you're going to want to stick with the things that do work in both implementations if you're sharing your code between .NET and Mono. So how do you know when a GC is actually happening in your application? Well, it turns out that the system will output debug information into your debug log every time a GC occurs. And in Xamarin Android, this is turned on by default because it's useful to see in Xamarin Android, again, because we typically are a bit more memory constrained on the Android platform. Xamarin iOS does not turn this debug logging feature on by default, but you can actually activate it yourself by adding two environment variables to your application. Specifically, the mono log level needs to be set to the value debug, and the mono log mask needs to be set to the value GC. You can use these same two environment variables in the desktop Mono environment, and so SGen, the collector that we use in Mono, is the same implementation in Xamarin iOS and Android as it is in the desktop. There are some features that are compiled out, so there's if-defs, but the actual implementation and the source code for it is exactly the same, and it's all open source, so you could go look at it if you want. In fact, the Start Here materials that are included with this particular class actually has a link to the source code for SGen if you want to go check it out yourself. It's all written in C and C++, and so you can kind of walk through that code and see all the algorithms and see everything that happens. But these two environment variables you set by going to your project options in your Xamarin iOS or your desktop app. You go to the general section, and then there'll be an environment variables section there that you can actually add both of these variables to. Once you do, you'll start seeing debug log events. The GC messages are all prefaced with the GC_ tag, and it will tell you a couple of useful bits of information. The first thing you'll see is what triggered this GC. So you'll know, for example, that the GC was triggered because the nursery was full. We'll talk about the nursery in just a moment. But the idea is we ran out of memory as part of an allocation, and so it triggered the GC. The second thing that it shows you that's useful to see is how long did the GC take? right? So we want to make sure that this value stays relatively low, because keep in mind that for the total entirety of this particular value here, 6 milliseconds, our app was not responding to the user. All right, so the lower the values, the better. We don't want to see really long values here because it indicates a potential performance issue with our application in terms of responding to the user. And so watch your debug output, and in particular, watch those total times for GC messages. So how long does a GC take? Well, it's really going to be dependent upon two things. The first is what type of GC is occurring. It turns out there are multiple types of GC that may happen in your application. And we actually refer to this as what generation has been collected in your application. The second thing is how many objects did the system have to walk? So remember, when we do a GC, it has to actually start at all your roots, and it walks every single reference that each root has access to. The more objects there are, the longer that walk is going to take. And so these two things really sort of define how long a GC is going to take. So let's look at both of these, but let's actually start with the generation. So it turns out that the algorithms used by the garbage collector rely on a premise that objects that have been allocated recently tend to be objects that we will be able to collect most often. And objects that have been around a while tend to stay around a while. And so the system divides your objects into two classifications. One is new objects that are allocated out of something called the nursery. .NET calls this generation 0. But the nursery is where where every object in Mono generally begins life. It gets allocated out of the nursery, and so what you'll find in the nursery is often objects that are temporary, things that perhaps were passed as parameters into a method, or things that a method allocated that it uses in the context of that method, or perhaps strings or IEnumerable objects that were allocated as part of a for each. These are all objects that are allocated, used, and then thrown away when they're finished. And so the GC, as part of the nursery collection, will collect a lot of these objects, and you'll see that that's predominantly the objects that get collected as part of the nursery collection. The second generation is called the major generation. Again, .NET calls this Gen 1, and things that sit in the major generation are objects that have survived at least one garbage collection. And so if it survives a collection, it moves out of the nursery and it moves into the major generation. Now, the major generation holds a lot of objects, and this is actually an unbounded memory segment. In other words, as we need more memory, we just allocate more memory to hold in the major generation. The nursery, in contrast, is actually a fixed size segment. So we allocate a block of memory, and it's always that size. And then as we allocate things, we end up doing a collection. We move all those objects in the major generation, and the nursery is empty, and we begin allocating objects again. So objects in the major generation, you tend to have a lot more objects here, and the objects tend to live a lot longer. All right, and so we're going to see sort of some of the algorithmic choices that the GC actually takes to kind of manage both of these generations. But let's sort of look at it in a more of a graphical approach. So again, let's take our example where we're going to allocate a block of memory in the nursery, in this case for a K object, and notice that we have a major heap. And we've got a bunch of objects in the nursery, and we're going to allocate K, but we don't have enough space, and so a nursery collection occurs. We identify all of the objects that are no longer alive by walking the roots. Really what we're identifying is the objects that are alive, and then everything else just goes away. Those objects go away, and then we actually physically move the live objects out of the nursery, and we copy them into the major heap. Now, this is a difference from .NET. So this is something that's known as a copy collector. And so SGen uses a copy collector as part of its nursery collection, and it physically moves objects from one spot to another. .NET, on the other hand, simply moves our pointer, and it kind of tracks Gen 0 and Gen 1 as one big segment. They call it the ephemeral segment. And so as you move from one generation to the next, it's not actually having to move the objects necessarily. It does potentially compact them, which is a memory copy, but they stay within the same segment. In this particular case, we don't even stay in the same segment. It's physically a different memory segment, and it moves from the nursery to the major heap. Now, how can we see this? Well, again, if we go back to our debug log, we can see how much memory gets promoted going from the minor generation to the major generation. So here you can see we promoted 5K objects. And the other thing that you can see here is how big is the major generation. So in this case here, you can see what the size of our major generation is. And that way you can kind of track in your log how big is that major generation getting. Because remember, it's unbounded. It grows to infinity, or at least to whatever the operating system allows us to allocate. The other thing that you can see is how much memory is actually in use in the major generation. So this is on a major collection. So notice here, the GC prefix is GC major versus GC minor, which is a nursery collection. And when we report a GC major collection, it shows us how much memory is currently in use by this application and how much memory was in use prior to the collection. So you can look at the two values and sort of contrast them. And if you see a continued growth in your major generation and it never seems to go down, then it's very likely that you have a memory issue in your app. What you really want to see is sort of growth and then release and growth and release. So how does the major heap actually get collected? When we do a major collection, it actually is collected less frequently than the nursery. So the nursery collections happen all the time. In fact, what you should see is a lot more nursery collections than major heap generation collections. And it's going to kind of look like this. Our application runs for a little while, and then it stops and does a nursery GC, stops and does a nursery GC. At some point, it decides it's going to do a major GC collection. And generally speaking, this happens in either one of two places. Either because there's not enough space in the major heap to complete a nursery collection. In other words, remember, we need to copy those objects from the nursery into the major heap. And if there's not enough space in the major heap, then it will attempt to do a collection first, and then if the collection still doesn't free enough space, then it will allocate another memory segment to hold the objects. The second reason is there is a heuristic at play here as well, and it is that the system allows the major heap to grow in terms of objects by about 1/3. And when it sees that it's exceeded that size, it will automatically trigger a major collection on the next GC that happens. And so it'll just sort of monitor that threshold. And when we exceed it, the system will automatically do a major generation collection. Now notice that we also do a nursery GC as well. So when we do a major collection, it's called a full collection, and the system does both the nursery and the major collection. Not together, but it does one and then followed by the other as it does the move. And remember, this is a stop the world collection. So while we're doing these collections, our app is not running. Now, Desktop Mono does have what's called a concurrent collector, and .NET does as well. And the idea behind a concurrent collector is that we can do some of this work, in particular, sort of the walk and find all our live routes, while the rest of our app continues to run. And so the system will identify safe points that we can stop threads at, and it will allow the GC to do at least the first part of the collection and allow the rest of our application threads to continue to run simultaneously until they hit a point where they perhaps need to do an allocation themselves, at which point they'll be blocked. Once the system has sort of identified all those routes, then it will stop all the threads and actually move memory around, because we can't move memory around while the application continues to run. But that's a concurrent collector. That's not implemented in the mobile variation yet, but it is in the desktop branch of SGen. So it's something that's currently being tried out, and .NET itself, the .NET GC, has a concurrent collector already. And so if you're using the desktop .NET system, then you're already using a concurrent collector. But be aware that that's potentially an optimization that may happen in the future. But today, at least on our mobile platforms, it is a stop the world collector. Now, how often should we see major versus minor collections? Well, generally a healthy ratio is about 1 to 10. That's not necessarily always going to be the case. Sometimes you may see it be lower, sometimes you may see it be higher, but you should definitely see a much larger ratio of minor collections to major collections. So here in my log, you can see I've got a major collection that occurred, and then I see a bunch of minor collections, and then I see another major collection. This is something to watch for in your debug logs. If you see a high or inordinate number of major collections, then you are allocating memory at a high rate that potentially could be an issue within your app. All right, or you're exceeding the nursery threshold very, very quickly. And again, that may be the case for your application. It's because it's going to be based upon your allocation patterns, but it could also indicate that you're holding on to objects, that you have a memory leak because it's having to do major collections more often, or that the major collection is taking too long. And so make sure to watch your debug log to be able to kind of check the ratio of minor collections to major collections. The nursery uses what's referred to as a copy collector, which moves all of your live objects from the nursery heap into the major heap every time the nursery gets collected. And ultimately what that means is we end up with a free segment in the nursery after every collection, and therefore we just start allocating memory from it. The major heap doesn't work that way. The major heap often has a lot of objects that have lived a long time and are likely still alive. And so to do the whole walk of objects, starting with all your roots and walking through everything that you can access, that can be really expensive when it's on the major heap because there's a lot more objects here. And so what can happen is over time, we can end up with holes in the major heap where objects have died and been collected as a result of a major heap collection, but other objects were further up in the heap. And so you can see here that we've got a bunch of dead space in the major heap itself. And this can make it harder to actually allocate memory because we don't have as big of a contiguous space. And so to combat this issue, sgen does two things. First, it organizes the major heap into buckets of various sizes. And when there's a minor collection or a nursery collection, each object from the nursery is copied into a specific bucket based upon the total size of the object. This allows the system to efficiently compact memory together and have knowledge of the size of the block so it can determine how expensive it's going to be to actually compact that particular bucket. Second, when the nursery reaches a certain fragmentation threshold, which is set to 66% by default, sgen will initiate a compaction of that specific bucket by moving each object and fixing up the references. This is done on a bucket-by-bucket basis, and it's done based upon how fragmented that bucket happens to be. And so you can see here that we compacted those 4 objects together, and that provides a larger free contiguous space of memory that we can continue to put objects into when we do the copy from the nursery. And so this happens periodically. It does not happen on every collect. It's based upon determination that's done by the GC algorithms themselves. And so periodically it will do this compaction when it detects that the fragmentation rate is too high. Now, that brings us to an interesting facet of garbage collection, and that is that not all objects are the same. In particular, really big objects, which Mono defines as anything over 8,000 bytes, are really expensive to move. And so we call these large objects. And large objects, because of the expense of moving them, even from the nursery into some other location, is too prohibitive. The system does not ever allocate these in the nursery. Instead, they are automatically moved to what's called the large object space in Mono. And so they begin life in a completely different heap, and they never leave that heap, so they're never moved. The large object space is never compacted. So memory is allocated and freed as necessary to be able to hold these objects, and it is collected, so objects do get freed and segments do get freed from the large object space. But the memory itself is not compacted because it's too expensive to move these. .NET has a similar heap. It's called the large object heap, but the actual size of the object is significantly higher. So in .NET, it's an 85K threshold. So if the object is over 85K, then it moves to the large object heap. In Mono, it's just 8,000 bytes. And so it's a much smaller ratio, which is helpful on the mobile platform where we don't necessarily have as much memory to allocate anyway. We collect the large object space on full collections. And so anytime that we do a full collect of the system, the large object space is scanned and the system will automatically throw away pages that are no longer in use. So that brings us to what do the memory segments actually look like. So I mentioned that the nursery segment is fixed in size. The default is 4 megabytes. And so the system allocates a 4 megabyte segment, and this becomes the nursery, and this is where most of our objects actually start out. They're then moved into the major segment, or the major heap. This is allocated in 16 megabyte chunks as needed. This is periodically compacted, and we do release segments when they're not used anymore. However, be aware that it's not immediate. The system holds on to some of the memory and puts it into a free list, and then as that memory is no longer being used, over time it will begin to free up the free list to reduce the working set of the memory of the application itself. And then finally, we have the large object segment. This is allocated as needed and it's never compacted. And again, we do free this as well. So when a segment is no longer needed because we freed a really large object, then the system will throw that away. Now, the things that typically get put into the large object segment often are things like arrays, because arrays in managed languages are always allocated contiguously. So if you allocate, say, for instance, a 10K array of bytes, it would be automatically allocated into the large object segment. I've changed our application slightly to be able to allocate and hold on to some of these objects. So notice that I still have our dummy class here, but now I've got a struct that I'm going to hold it in, and I'm going to put that struct into a list. Now, the list itself is allocated on the GC heap, but it allocates an array, and all of these objects right here are going to be allocated as part of that array. And arrays are always allocated contiguously. And because I'm going to be allocating, it looks like 1, 2, 3, 4, 5, 6, a million of these objects, this is large enough to where this is going to end up on the large object space. Okay, and so it won't show up in our memory allocation itself. And the idea is I'm still going to write out to my GCalloc CSV, but I'm going to allocate a million of these objects, and I'm going to hold on to these objects. And so because I'm holding on to them, these objects are going to get promoted to the major heap. And my goal is to take the address of the object when it was in the nursery, and then to take the address of the object again when we're actually ready to get rid of it. And what we should see is a difference between those two addresses. In other words, we'll actually see the copying from the nursery into the major heap. And so let's go ahead and run this. And so you can see it's allocating. And I'm also seeing all of the GCs that are occurring here because I turned on the GC Alex in my environment variables. And so I can see I got a bunch of minor from nursery full collections. And then at the very end, we did a GC major because we had a user request. That was me requesting that. And you can see how long it took. So notice this was a 5 millisecond pause versus all these nursery collects where it was just 0.15, 0.17. So the major collect was very significant in comparison to the nursery collects. But let's go look at our data itself. And so I'm going to go ahead and open this data up inside of Sublime, which is just a text editor, just so that I can see it. And so remember, this address here was the address in the nursery, and then this address over here is the address on the major heap. And what I want you to notice is the pattern that actually happens here. So again, you can see that we just have an increasing value that's going up here. So 304 to 320 to 336 to 352 to 368 to 384 to 400 to 416. So essentially it's 16 bytes. That's the integer plus the object size itself. And so ultimately what we're seeing here is how big that allocation was of that dummy object. It's 16 bytes. There's a 12 byte overhead for every object plus the 4 bytes for my integer. And you can see that same pattern here. And notice that it's contiguous. In other words, 128 to 144 to 160 to 176. These are compacted together when it gets moved into the major heap. If we graph this, we should see very similar heuristics to what we saw from the original collection when it was just on the nursery itself. And so now I've got both of these columns. Let me select both of them and let's go ahead and insert our line graph. And so you can kind of see the allocation range here. Now notice that on the nursery side, we're seeing the same memory being used over and over. But on the major heap, what you're seeing here is it goes up and it never comes back down. And so we see these little drops here, but the reality is the memory address is continuing to move up as we continue to allocate memory. Because remember, the major heap is going to continue to grow as we continue to allocate memory, unless we just release a bunch of objects all at once, which we did not do in this app. We held on to all the objects. And so hopefully this kind of gives you an idea of how the nursery and the major heap kind of work together in order to hold our objects. So what can we do in order to help out the garbage collector? Well, recall that static fields and properties are always root objects. These are always objects that will keep things alive, or always references that will keep things alive. And so if you have a transient value which is static, for example, here we're using it to inject a value without an instance into our application class, then you should release that reference by setting the static to null when you're done using it. The same is going to be true of class fields and properties. If the class is finished using the value, then it can set the property or field to null to allow that reference to be collected on the next GC. Now keep in mind, this is only going to help if the owning parent object outlives the child object. If they have the same lifetime, then there's no benefit to setting the field or property to null. And also, the second point I want to make here is GC is only interested in reference types. So we aren't talking about value types or simple things like numerics or structs. Those things are always allocated in place. So for instance, if it's an instance field of a class, then an integer would be allocated as part of the size of that object, not independently by itself. And if it's an integer that's actually part of a method, then it's going to be allocated as part of the stack of that method. And so these sorts of objects are not allocated by the memory allocator by themselves, and they're also not collected by the GC by themselves. They're always done as part of an owner of some kind. Now, the other thing that is useful to think about when you're setting things to null is async and iterator methods. So those sorts of methods, when you use the async keyword or you use the yield return keyword for an iterator method, those generate state machines. And those state machines often will pull values that are in the method into a class that's then allocated on the GC heap. And so again, if you've got a case where you've got values that are being used in the context of one of those state machines, but it's not used to the very end, it can be useful to set those to null once you're done using them. Now, one thing that people sometimes get confused about is whether or not they should set values that are used inside of a method, in other words, allocated in the method and used in the method, to null. Generally speaking, the answer is no. .NET's JIT compiler is very, very smart, and one of the things that it does is it generates look-aside tables that indicate when a variable that's used in the method is no longer in use. And the GC will consult those look-aside tables to be able to determine whether or not something can be collected in release builds in the middle of a method. Mono doesn't do that today, so be aware that the Mono JIT compiler isn't capable of generating those look-aside tables, and so values in Mono, when you're using the Mono runtime, always live to the end of the method. So if you're concerned about that, or you have large values that are being allocated and used inside of a method, but they're not used to the very end, you can set those values to null, and you will get potentially a slight improvement when you're using Mono. But the reality is it's probably going to be imperceptible from an application perspective, and so I would only advise that if it's a really expensive resource that's been allocated. And the reality is it's very likely that Mono at some point will implement the same optimization that occurs in .NET, and it will be unnecessary at that point anyway. Now, one of the things that happens when we talk about garbage collection is we have to think about when objects get collected. And the best case scenario, and what we really want to have happen in a GC-based system, is we either want our objects to live a very short amount of time and die in the nursery, so allocated in the nursery and get collected as part of the next nursery collection, or we want them to be promoted to the major generation and live forever. One of the two. Those are the two best case scenarios. The worst thing that could happen is this scenario here. So notice that my nursery is full. I'm going to allocate K. I have my major heap here. And it turns out that all of these objects here were allocated inside of a method, and I'm using them as part of some sort of memory-intensive algorithm. And so when a GC occurs, we've run out of space, a GC happens, and we end up promoting all of those objects into the major heap because the method is still using them. And then we exit the method, and suddenly all of these objects are dead. Now, this is a problem because now they've been promoted. We took the expense of copying them all into the major heap, of fixing up all of the pointer references, and now suddenly we don't need them anymore, but they're taking up space. And keep in mind, major heap collections don't happen all the time. In fact, they happen very rarely, or at least we want them to happen very rarely because it's expensive to collect the major heap. And so now what we've done is we've created somewhat of a midlife crisis in our application. We've got a bunch of objects that got promoted and then immediately died. This is the worst case scenario that you can possibly have with a GC-based system beyond a physical memory leak of some kind. Because now these objects are going to live a lot longer than they should. So what can we do to fix that? Well, there's two things. The first thing we can do is if you know you have a method that's going to allocate a bunch of stuff and you want to try to ensure that it does not have a GC in the middle that promotes all those objects, you can put a GC collect before you call the method. This will ensure the nursery is empty, and therefore it can try to prevent a midlife collection while the method runs. Now, of course, this isn't going to be an absolute. If you exceed the size of the nursery, you're still going to get a collect and we still have the same problem. So this doesn't stop a collection from occurring, it simply reduces the risk of a collection from occurring. So what else can we do? Well, it turns out that the sgen collector for Mono actually has some knobs that you can twist and tweak in order to sort of control some of the aspects of the collector. Now, this is very specific to Mono. This doesn't work in .NET, and .NET doesn't have any corresponding capabilities like this. But we have an environment variable called mono GC params that you can set in your application that will tweak the GC settings. And the first thing that you can tweak is the nursery size. By default, it's 4 megabytes, but you can set it to be whatever size you want. And so, for example, here you can see that I'm changing my nursery size to be 8 megabytes. And so therefore, I'm going to reduce the number of nursery GCs that happen in my app because now it's going to take longer for that nursery to fill up that then causes the GC to occur. Now, the expense of this is I'm going to increase my memory pressure. My working set's going to be higher because I'm going to be holding on to objects longer because I'm not going to collect them as often. But if you run into a case where you see a lot of minor collections and a lot of objects being promoted and then a lot of major collections happening after that and you see all those objects going away, this can be one way to stop that from happening. So if you know that your application has that particular allocation issue, you can bump the size of the nursery in order to make sure that your routines that run have enough nursery space to prevent a collection from occurring while the method executes, and instead push it off until after the method is finished, and therefore everything gets collected as part of the nursery, which is much cheaper. The second thing that we can set is something called the soft heap limit. And again, this is set to a number of bytes. And both of these fields are bytes, and you can use suffixes like K, M, and G in order to actually say you want it to be in kilobytes, megabytes, or gigabytes. I would definitely say gigabytes is a bad idea for most apps, but it does support suffixes on the values, or you can just say a total number of bytes and don't put a suffix on it. Now, what soft heap limit does is it actually sets a target working set for your app. What that means is that the GC will optimize for performance until it hits this size. And so it monitors the overall memory being used by your application. And once you exceed this value, it begins to be more aggressive about doing major collections. And so it will collect the major heap more often when you go over the soft heap limit value. So the higher this value, the less often a major collection will occur. The default value for this is -1. In other words, it always optimizes to do collections over performance. So if you set this to a value, what you're essentially saying is, I want to allow my app to use up to this amount of memory before you start being aggressive about doing major collections. And once we go past that, then I want to see if you can get me down below that threshold. So you can set the soft heap limit. The third thing that you can set is something called the evacuation threshold. This is the percentage of fragmentation that we want to allow in the buckets in the major heap. By default, this is 66, but again, you can adjust this value by either raising it or lowering it to be able to say, I want to allow more fragmentation or less fragmentation. If you say more fragmentation, then again, it won't compact the major heap as often. If you say less fragmentation, it will compact the major heap more often, but it will keep your objects closer together, and so you may get a benefit just from cache coherency. And so these three values can be placed into the mono GC params environment variable. They're just comma separated, and then you set the values as a environment variable for your iOS or your Android app or your desktop app for that matter. And then it will use these values instead of the hard-coded ones that are actually in the source code itself. Now, Android is a little bit interesting because it does not support that environment variables box that you saw earlier for iOS. In iOS, you would just set that as part of the runtime settings of your app. In Android, we have to add something called an Android environment file. This is a simple text file. Notice I've added a file called environment.txt to my Android app. And in that file is just a set of lines. So it's just, again, text, where each line represents a specific environment variable you want to set. And then it's just value equal, or key equal value rather. And so here you can see we're setting our mono GC params to nursery size equal 8K, evacuation threshold equals 75%. Now, the key thing to this is in order to make that text file in an Android environment file, you have to set the build action. So right click on the file and then go to build action and set it to Android environment. This is what will turn it into an Android environment file. And the system will read this at startup and it will apply all of these values as environment variables, and that's what the system will use as it runs. So let's try out a couple of these, or at least one of these environment variables to see what impact it has on our application. So here's our little application again, and I'm going to go to the project properties for this. And since this is an iOS application, I can just add environment variables right here under the Run General section. Again, remember, if it's Android, you're going to actually have to add an Android environment file. So I'm going to say mono GC params, and I'm going to go ahead and set this to nursery size equal, and let's go ahead and set it to 8 megabytes. The default is actually 4, and so this will double the size of the nursery. And so let's just see what happens in our data as a result of that. So again, we're going to run this for 3 seconds. It's going to generate a file, and then let's go graph that file with Excel. So I'm going to go ahead and select all this, and let's just go ahead and create our same line chart just to see if there's any difference in the data that we saw before. Now notice this one looks a little bit different. We see the same pattern in that we see a bunch of memory allocs, and then we see the GC collect, which drops off the memory, and then we see a bunch of memory allocs. But notice that this time we have far fewer nursery collections. In fact, there was just one while our app ran. So we just had one collect as opposed to, say, 3, 4, or 5 that we saw in the previous example where we were allocating objects. So these sorts of tweaks that you can do via these GC parameters can affect the actual application heuristics of when a GC runs and how long it's going to take. Now clearly, this one here is going to take a lot longer because we're going to have a lot more objects to walk through and collect potentially. And so by upping the size of the nursery, it means A, we're going to be using more memory in the nursery, and B, it's very likely going to take more time to copy live objects from the nursery into the major heap. And so you have to be a little bit careful, and you have to look at some of your parameters just to see what happens in the application itself. So now you've seen sort of the basic premise of the GC-based system. And we've sort of walked through the algorithms that are in use, when a GC happens, and how you can monitor the GCs that are occurring in your application. This is really useful information to you as a C# programmer because it lets you know exactly how your memory usage is occurring in your app and to be able to diagnose potential memory issues prior to you releasing your application. We recommend that you take the next class in this sequence, which is CSC271, where we talk about how to clean up non-memory based resources, and specifically using finalizers, another construct of the GC, and the iDisposable pattern. And then the other class that you should look at as well is XAM370, which looks at common memory pitfalls in your Android and iOS applications. And we're going to leverage some of the knowledge that you've learned in this class in XAM370 to be able to see some of the common issues that you'll have in iOS and Android because of the GC-based system. So thank you very much for attending this class. I hope this was helpful for you. Again, my name is Mark Smith. You can email me at the email address that's listed here on the slide if you have any questions, or of course you can use the Xamarin University forums. Thank you very much for attending this class, and I hope you have a wonderful day.